Excellent. Some of you have been asking me about the videos, and I am slowly putting them on YouTube. The link that I put on Slack, that is the correct link, and I just keep adding them every single week. So soon you'll have up-to-date videos. I'm not going to fall too far behind, so don't worry. So the agenda for today is the following. The first thing we are going to do is learn and use the Python module called Sci-kit learn. So SCI-KIT, Sci-kit learn. Sci-kit learn is going to be our pandas for machine learning. So for pandas, we use pandas for data exploration, and we're going to use Sci-kit learn to actually do the machine learning. So last time we talked about KNN. Today we're going to be doing KNN with the built-in Sci-kit learn package. And we're going to see the differences between you building your own and us using Sci-kit learn. So we're going to learn Sci-kit learn, which is going to be a basis for machine learning for the remainder of the course. After that, we're going to talk about the article that I asked you guys to look at, the bias variance article. We're going to talk about what bias and variance are. And these two are also going to be very high-level concepts that will be discussed pretty much every day going forward. So bias and variance are two very theoretical things. They're not coding things. They're not math things. They're just ideas. We'll do some code on mammalian data to talk about the difference versus bias and variance. And then we're going to get into model evaluation. So like I mentioned, so in the 5 steps of the data science workflow, we explore our data, we build and evaluate our models. So we built models last time, we're going to build models today, and we're going to talk about how we evaluate our models starting today as well. So pretty much all 3 of these items, in fact, all 3 of these items, without fail, will be brought up in almost every single class moving forward. So like pandas will be continuously relevant, so will all 3 of these things moving forward. If you haven't done so already, please upload your homework, including your code file and your 1-pager, to your sfdat17 work GitHub repository. Many of you have been asking us Git questions, so thank you for that, for asking questions and not just not doing it. It's very, very important that you upload to the GitHub repository because that's where we're going to look for your homework. If it's not there, you didn't submit it to us. All right. Also, if you haven't done so already, please Slack David. Sorry, I put this on you. Please Slack David your GitHub handle along with your name if you haven't done so already. If you've done this already, please don't do it again. He doesn't need all of those. If you have not done so, please give a Slack message to David with your name and your GitHub handle so we can easily find it. And then we'll all grade it from there. Okay. Any questions before I begin? Cool. Cool. We will begin with code today. The first thing I will be looking at is a code file called 06_sklearn_knn.py. This, of course, is in the code folder if you update your GitHub repository to be updated with my own. I will ask, again, as I always do, can people in the back, is this too small? I'm not getting a no. I'm getting no, so it's not too small, i.e. it's fine. That's what I'm getting pretty much? Okay. Yeah?
You want lights turned down?
Yes! Let me do that. Thank you.
This is the one I think.
Is this better? Okay. No, I guess it is better. Okay. So, last time I asked you to build a KNN from scratch. Now, can someone remind the class, what is KNN? I'll start simple. What does KNN stand for? Someone raise your hand and tell me. What does KNN stand for? Someone. What does KNN stand for? K nearest neighbors. Can someone else please raise your hand? Can someone else tell me why it's called K nearest neighbors? How does the model work? Explain it as if you were explaining it to your parents, who I assume don't do data science. Well, I guess that's a bad assumption. How would you explain this to someone who does not know data science? How does KNN work? How does K nearest neighbors work? Someone raise your hand and tell me. Lou, tell me, how does it work? Give me an example, not using data points and numbers, but give me an example in real life how you compare K and N to someone learning in real life. Or anyone, if you have an example, please tell me. What's an example? We use this. Birds of a feather flock together. Which essentially means, if it walks like a duck and it talks like a duck, it's probably a duck. For those of you who are not familiar with idioms, I apologize. But essentially, if it acts and talks like something else, it's probably that thing. And this is a very common technique for biologists when trying to classify new species. They say, okay, does it have 8 legs? Yes. All right, it's probably an arachnid. All right, does it have, is it a black body? Fair enough. Does it have a red mark on the back? It's probably some type of black widow spider. So they use, what is it similar to try to classify what it is. All right, so now we're going to be using K and N in the terms of Sci-kit learn. Sci-kit learn is a module in Python built by a human just like pandas. So this is something that someone else wrote, and now we're just using it. So the first thing we're going to do, we're going to import pandas, because we still need pandas to manipulate our data. But Sci-kit learn is going to take in a data frame and perform machine learning on it. Iris is so popular that it is actually a built-in method in Sci-kit learn.datasets. So Iris is so popular that whoever built Sci-kit learn actually included Iris as part of the module because it's used so often. So in line 8, from sklearn, which is the abbreviation for Sci-kit learn, from sklearn.datasets import load Iris. So I will make my load Iris. And if you look at it, we have this very interesting NumPy array, 2-dimensional NumPy array. Hopefully at this point, Iris is not so much of a stranger to you because we've been using it a lot in the past couple of days. Okay, now if you want, and what I'm going to do is on line 13, I am going to read in the data as a CSV from the web. So I'm making this distinction because there are 2 ways of loading Iris. You can either load it directly from Sci-kit learn, and if you do so, it comes to you not as a data frame, but as an n-dimensional array in NumPy. If you choose to read my CSV with pandas, you will automatically get a data frame. Most people tend to choose the data frame structure because it's a little easier to work with and it has more capabilities of manipulation. So I will more often than not be using the data frame as opposed to an n-dimensional array. But it's good to know that Sci-kit learn accepts both. So at this point, it's actually a decision on your end which one you want to use. I will be using, for the most part, data frames. So I'm going to make 2 new variables, an x and a y. This x and this y are similar to the x and the y that I used on Monday about the predictors and the response. So x is actually going to be my predictors, and y is going to be my response. Can someone remind the class, raise your hand, what are the predictors? What do they do? I'll ask the easy one first. What's the response? What is the response? When I keep saying that word, what is a response? And this is a word that you should all be very familiar with going forward. What is a response? Someone, what is a response? It's the, I'm sorry?
The outcome?
The outcome, yes. It's the thing we're trying to predict. It's the thing that I actually want to predict. All right, I said the word predict. Bells should be going off in your head. Because what type of machine learning are we doing if I have to use the word predict? Someone raise your hand and tell me. What is the type?
Structure.
Say it again? Not structured. It's an S word. Supervised. Supervised machine learning is synonymous with predictive analytics. So when I do predictions, I'm doing supervised machine learning. And the response, in this case I'm calling it y. Y is the thing I'm trying to predict, which is, in the very specific case of Iris, what? What am I trying to predict? The species, the type of iris that that's the thing I'm trying to predict. So what is X? So we got Y. What is X? X are our predictors. What are predictors? Someone, raise your hand down. What are predictors in general? Yes, Luke. The factors that contribute to it. In other words, the things that I'm going to use to predict a response. What I think are relevant in knowing if I want to predict the response. They're my independent variables. They're my features. Those are other words for predictors. In the specific case of iris, what are the predictors? What are the predictors in the specific case of iris? The response is the species. What are the predictors? How many are there? 4. What are they? What are they? Sepal width, sepal length, petal width, petal length. Those are our 4 predictors. We're going to use those 4 things to predict the species. So can someone give me an educated guess? X dot shape. What will X dot shape be? What is dot shape? What does it tell us? Say it again? So how many rows and columns? How many rows are in X? How many observations are there? 150. How many columns are there?
4.
So it's 150, comma 4. There are 150 rows and 4 columns in the predictors. Now, the Y shape, how many observations are there? How many species do we have? Well, there are 3 distinct species, correct. But how many observations of species do we have? Not distinct. Still 150. That number has not changed. How many columns are there, though? 1. In the dot shape, if there is a 1 in the columns, it actually doesn't put the 1. So when you see 150 comma, it's the same thing as 150 comma 1. So that's not an error. That's just the way it tells you that there's... Because the idea is there is no column because it's a series. That's the one caveat. So when you see this, it means you're looking at a one-dimensional object. So there's only 1 column, just to be clear on that. So good job. Now, let's see how easy it is to do machine learning with Sci-kit Learn. There is a very set, how should I say, almost agenda when using Sci-kit Learn. And it looks like the following. I will import the class, line 22, from sklearn.neighbors, import kneighbors classifier. So we have this kneighbors classifier that we just imported. Line 24 is the next part, instantiate. So we imported the class, now we're going to instantiate. What does instantiate mean? It just means create one. It just means make one. So the import doesn't make anything, it just makes available to us. In line 24, I'm actually creating an object. And I'm calling it lowercase knn. Knn equals kneighbors classifier, and I give it a single parameter. N neighbors. What is n neighbors? Someone tell me, what is n neighbors? N neighbors is the number of neighbors we're going to look at to make our prediction, right? On Monday, I called it K. In Sci-kit Learn, they call it n neighbors. Why? Whoever wrote it decided to call it n neighbors. End of story. It was a decision made by the person who made it. So import, instantiate, fit is the third one. Fit. Line 26. knn.fit. Now, knn is an object of our own creation. Think of it like a blank slate. When I create knn equals kneighbors classifier n neighbors 1, what I'm saying is this is an object that at some point in the future will be doing knn with n neighbors 1. Line 26, the highlighted one, line 26 is taking that blank slate and giving it two things. The predictors, comma, the response. So far, so good. We're giving the blank slate. Here are the predictors, the things I'm going to use the predict with. And here's the response, the thing I'm trying to predict. So once I fit line 28, we'll take that KNN object and predict something new. Import, instantiate, fit, predict. So I give it 3, 5, 4, 2, which is sepal length, sepal width, petal length, petal width. And out pops Iris virginica. Congratulations, you have performed machine learning in 4 lines of code using Sci-kit Learn. And that's why we really love Sci-kit Learn in the Python community. If you ever go to a data science meetup in the world, chances are at some point they're going to use pandas, and definitely they're going to, if there's a machine learning one, they're definitely going to be using Sci-kit Learn. This is our favorite machine learning module, rather, not model. Are there any, yes?
So is there an X because n neighbors is equal to 1?
Is,
Assume if you have like another value there.
good question. The question was, does the n neighbors variable have anything to do with how many parameters I put into KNN? Is that correct, the question? The answer is no. Can someone tell me why? What is n neighbors? What if I made it 7, for example? Ozzy, what's...
So what we'll do is we'll look at that. Look at 3, 5, 4, 2.
Uh-huh.
We'll look at the closest neighbor in X.
Sure.
Then we'll predict Y.
Yeah.
So like if you had 7, if you had n equals 7, right? N equals 7. This would make 7 closest neighbors.
So does that change the predictors or the response?
Change the response.
I would argue no.
Change K.
If I change k, the data doesn't change. The procedure will change. The procedure is the thing that KNN does. X and Y are data. Data will not change just because I tell it to look at 1 neighbor versus 80 neighbors. The data is still the data. The only difference is that KNN, instead of saying, here's the 3 closest neighbors, oh, here's the 20 closest neighbors. But the data doesn't change at all. Does that make sense? And no matter how much I change n neighbors, the data, x and y, don't change. And all a supervised model needs is a predictors, set of predictors, and a response. That's all it needs. This n neighbors equals 1, that's called a parameter. So models, so KNN is the model, to put it in terminology. KNN is the model. And neighbors is a parameter. X is the set of predictors. And Y is the response. So to put it in machine learning terminology, X and Y are the predictors and the response. KNN is the model. So when someone says, what model did you use? You would say KNN, k-nearest neighbors. And now when they ask you, well, what was your K? They're asking you, what parameters did you input? Now if you say 1, your parameter is 1. If you say, I use 10 neighbors, you're changing your parameters. Your parameters are what dictates how the machine learning model works. Changing your parameters does not change your data. Your data is static unless you manipulate it in pandas or do something else. Add columns, delete columns. But the machine learning model won't change your data. It will use your data according to the parameters. They're separate. Does that make sense? Cool. And this idea becomes hopefully very clear throughout the next several weeks. I can input several predictions at once. So here in line 32, I have this variable called x new. X new is a list. It's a list that contains two lists. Each list, think of each list as a flower. Because a flower is a set of four numbers: sepal length, sepal width, petal width. So x new actually contains two flowers. I can put that list into the predict function, and out pops my two predictions, Virginica and Setosa. Let's try it with a different value of k. So now I'm changing the parameter. I have to instantiate a new model. If I want to change a parameter, I must create an entirely new model. So I'm rewriting k and n to be k neighbors classifier, but instead of n neighbors equals 1, n neighbors equals 5. I will instantiate, I will fit, I will predict.
Why do you need to fit it?
Because I made an entirely new model, which means I made an entirely new blank slate. Every time I instantiate a new model, I have to refit it to the data. I can't just change a parameter. I have to make a new one with new parameters and then fit it again. Good question. The question is, what's happening when I fit? It depends on the model. So for k and n, fit, how about you tell me? In k and n, what does fit mean? What does it have to do with all the points? Find the distance between what and what? So the distance only happens when? When do you need to calculate the distance? When there's prediction. When there's a new flower, the 151st flower, that gets compared to all 150. But before the prediction, there is no need for distances. So actually in k and n, fit, all fit does is put the data in rows, so that when the new flower comes in, it's ready to do the distance for all of them. In later models, more complex models, for example, next week when we do linear regression, fit will actually calculate the line of best fit. That's what fit will do. So depending on the model, fit does something different. But in all models, fit means take the predictors, take the response, and do whatever math necessary to create your prediction algorithm. In linear regression, fit will make a line. And later on, in decision trees, fit will build a tree. So fit does something different depending on the model. In k and n, it's the easiest one. All it does is prepare them to do the distance formula by setting everything to a float and making sure they're in a row column structure. It is very basic stuff just to prepare it for the distance formula. These three lines of code I'm highlighting, I want to make sure that these are very clear to everybody, because they're the most used lines of code in Sci-kit Learn. The only thing that will really change are what you call your model and the parameters. So when I make a k neighbors classifier, I'm calling it k and n. Why? Because I want to call it k and n. It's a variable. That k and n is now a blank slate. All it knows is I'm supposed to be a k and n. As soon as I say fit, it then takes an x and y and prepares itself for prediction. And then I say predict, and I give it the 151st flower, the flower that it hasn't seen yet. Predict proba is a very nice method as well. Predict will just tell me, oh, it's a versicolor or it's a virginica. Predict proba will actually give me the probability distribution for each class of flower. So it's actually telling me the probabilities for each class. Because in the end, there's three classes, right? there's 3 classes. And if there's an 80% chance of one and a 20% chance of the other, it's going to choose the 80% class. How does it know which one to pick? Whichever is the highest. What if there's a tie? Random. Which is why we don't usually like even numbers for our n neighbors, because it's easier to have a tie in an even number. So, what am I looking at? What am I looking at? I have a row column structure, and this is what happens when I do predict probabilities. Each row is dedicated to a flower. So x new, recall, takes in 2 flowers. The flower of 3542, and then the flower of 3522. 2 flowers. The first row is the first flower, the second row is the second flower. Each column is for the species. So the first one, is Setosa, the second one is versicolor, and the last one is virginica. So it's Setosa, it is, yes, I'm crazy. Setosa, versicolor, virginica. I'll write that down. And this is the order. Setosa, versicolor, virginica. How do you know the order? It is in the same order. Oops. I'm crazy. Oh, I'm sorry. It's not. It's in the, if you do y dot, it's the same order as it would be when you import the data. So it's Setosa, versicolor, virginica. So, the top left number, which is a 0, what that's saying is the first flower has a 0% chance of being a Setosa. So we have flower 1, flower 2. The first flower has a 0% chance of being a Setosa. The first flower, this middle number, has an 80% chance of being a versicolor. The first flower, the number in the top right, has a 20% chance of being a virginica. So what wins? The versicolor. For the second flower, the bottom left number, means there's a 100% chance it's a Setosa and a 0% chance everywhere else. That's what those numbers mean. So when it comes down to predict, it just picks the highest probability. So the first flower became versicolor, and the second flower became Setosa. Where do those numbers come from? Ozzy, where do the numbers come from? They are exactly the proportions for k nearest neighbors. So 80% just so happens to be 4/5. And we're using neighbors of 5. So what this is telling me is that for the first flower, of its 5 nearest neighbors, 4 of them were versicolors, and 1 of them, 20%, 1/5, was a virginica. Which is why 80% chance of versicolor. This 100%, that means of the 5 nearest neighbors to flower 2, all of them were Setosa. So its prediction is Setosa. It could have come out the following way. It could have been something like, for example, 40%, 40%, and 20%. If this were the case, it would just pick a random flower, versicolor, for example, or virginica, it doesn't matter. That's how it works. Any questions? Yes.
So you have to load your data in with y values in order then, or else it won't know the index?
Good question. The question is, do they have to be in order? Yes, but I don't think the order you're thinking of. The only order you need is, if I have x and y, and let's say y says Setosa, and the x is like, 1, 1, 1, 1, and then 1, 2, 2, 1, and this is a virginica or a versicolor. The only order is that when these are two separate variables, the first element of x must correspond to the first element of y. The second element of x must correspond to the second element of y. The order in which they occur does not matter. But as long as you preserve, down here at the 51st row, the flower in row 51 of y should match to the 51st row of x. They have to be there.
Just mean for the predict proba, like if the Y's were all random, would it know like column 1, 2, 3 is Satosa versus color?
Good question. There is a way, I'm going to ask my TAs really quick. What is the, I actually forgot, the way to get the feature names out of KNN? You know what I mean? Yeah. There is a way to get the name of them in order. Classes. KNN.classes. There it is, and I'll show it again. If you do knn.classes, it tells you the order. Thank you for, I should add that into the code base for next time. .classes will actually tell me the order at which it's telling me. So, let's see, Satosa, versicolor, virginica, Satosa, versicolor, virginica. It's the same one that I told you before. So it's .classes underscore. Yes?
What code did you type prior to that process?
What code did I type?
This is the function right before that.
The clear function?
Class's name.
Oh, this is kind of an advanced Python trick, and it's actually a fun fact. If you take any object in Python and you do dot underscore underscore dict underscore underscore, it actually shows you that object as represented by a dictionary. And all objects must have it. So if you ever have an object that you're dealing with and you want to learn more about it, just do dot underscore underscore dict underscore underscore, and it will force the dictionary representation of that object. And I did that, and I saw that one of the keys was called classes, and its values was this. So then I knew that dot classes gave me this. Does that answer your question?
Yeah.
Cool. I'm going to add that in. Yeah.
And so I think when you're in the console, you can actually create an object with not tab, I think. So that Python should also pop up.
You can, and I've done it before, and it's messed up my spider, so I'm not going to do it. But there is a variable explorer. Is that what you're referencing?
Yeah.
The variable explorer, and also Rodeo has this too if you're using Rodeo. Rodeo and Spider both have a variable explorer, which essentially you can click on the object and like look around it. But I'm not going to use it because we're hardcore in this class. I use advanced Python things like .dict. And there's other ones too, which I don't know all of them, but there's a lot of them. A lot of hidden Python stuff. All right, so 1 neighbor, 5 neighbors, 20 neighbors. Which one do I use? Because the whole point of this is I need to make a model that works. And it's one thing to explain it, but it's another to use it. So there are many metrics for deciding which is the best model. And metrics is a very common theme that will come up in this class a lot. The most basic metric for classification is called accuracy. Accuracy is exactly what you think it is. It is the percentage of times that your model is correct. Done. It is the percentage of times your model is right. So if it says versicolor and the answer was actually virginica, wrong. If it said Satosa and the actual answer was Satosa, right. Accuracy is the number of right divided by the total number of times you tried. That's your accuracy. That's how you're graded on most things in life. There's a way to get the accuracy out of a KNN model. For clarity purposes, I'm going to start from scratch in the instantiate part. I'm going to instantiate a new KNN. I'm with 5 neighbors. I'm going to fit it to x and my y, and then I'm going to score it on my x and my y. What does score do? Score will go through each element of my parameters. In this case, I gave it x and y. And it's going to, for each x, it's going to predict it. If the prediction was the same thing as the y, which is the second variable I gave it, if they're the same, you know, there's like an internal variable called right, plus equals 1. Else, wrong. I'm making my own variables up. That's how it works. Score will take in, and it looks very similar to fit, right? It takes in a set of predictors and a set of responses. It's going to, for each of the predictors, predict it, and then compare it to y. If they're the same, right plus 1. If it's not the same, wrong plus 1. So what this number is, 0.9667, or 97%, what it means is, of all 150 observations in KNN, it tried all of them, all 150. And 97% of the time, our KNN model was right. And the other 3%, it was wrong.
So it's using its own data set as the predictors and seeing how it goes, right? When it knows what the answer is.
Correct.
Question is,
Sure. The question was, I'm giving the score the same data as I'm giving the fit. Is that what you said?
basically,
Yeah.
you're doing the predictions on something you know the answer to, and if it gets it right, it's counting it. Is that right?
Correct. So, well, you're correct, and here's why. And imagine again the very simple example of any test you ever took in school. If I'm going to test you on something, I need to give you questions to which I, Sanan, already know the answer to. Because otherwise, how can I give you a grade if no one knows the answer? So score can only work if I'm giving it data to which I also know the answer to. Does that make sense? Yes.
Does it score the all exact value? Like, does it compare 1 to all 150 or 1 to the other 149? Like, does it compare it to itself at one point? Because its own value that you're comparing is in the data set, right?
Good observation. Because I've given it the same data set as the fit, yes, at one point it will compare it to itself. And we're actually going to explore that a little bit later in the class today, is if that's a good thing or not. That's a good observation. So let's try it with 1. So keep in mind we have a 97% score for K. Now, your gut feeling says, probably, if you increase K, you are comparing the data point to more other data points, and your prediction should get better because you're learning from more things. So if I make a neighbors of 1, the idea is that's the worst one because I'm only comparing it to one other thing, and I shouldn't do very well. The problem is I get 100% when I score this. Why? You're going like, yeah. Why?
I'm assuming it has to do with what you just said. And essentially, it's saying, oh, what's the nearest one? What's that one? It's the exact same. That's reading.
It's exactly correct. That is exactly correct. So what just happened was the following. In the last 3 lines of code of this file, 53, 54, and 55, I made a new k-nearest neighbors with neighbors 1. I fit it, I trained it on x and y. So in terms of our terminology, my fit takes in my training set. When I score it, I give it a test set. So remember the training versus test? I fit it to the training, and I predict the test. In this case, the training and the test are the same. In that case, you can think of it like, it's like I took a test where the study guide was exactly the same as the test. Every question on this test I've seen before, therefore I know the answer. And that, my friends, is called overfitting, which leads us very nicely into the bias variance article that I asked you all to read. I'm going to ask you a very honest question. Please raise your hand if you read the article. Please be honest. Raise your hand if you did not read the article. I want you to, okay. It's about half of you. That's fine. Let's take a 15-minute break. For those of you who did not read the article, please take a chance to at least skim through the article so that we can have a very nice talk about it starting at 7:30. Let's take a 15-minute break. We didn't lose anyone. This is good. Well, we just lost her. Now she's gone. She'll be back. So I hope you had a chance to take a look at the article. Now, the article talks about several different things, but the two big ideas are the bias variance trade-off, that's one, and then the idea of overfitting, underfitting. So can someone tell me a little bit about bias and variance? What's the difference? What is bias? You don't have to give me a mathematical definition. You don't have to give me, something like that. What is the bias in your own words? Yes?
Here's the actual accurate thing looking like this, and then the bias is where.
Bias, I know she's your fist.
And then the bias is where your actual measurement is.
You said hopefully it's on top. Why?
Because it makes your model more accurate.
Okay, good. So bias, actually, you can think of bias as another term. It's really the difference between what your model predicts and where it should be. It's like an error. Low bias means your model tends to be very accurate. Hit the nail on the head. A high bias model tends to not be very accurate when it comes to predict. And you're thinking to yourself, well, why do we even like high bias models? Because they seem to be awful at predicting. Well, then there's this thing called variance. Variance is kind of the underdog of metrics. It's a very misunderstood metric. Variance, in very layman's terms, is kind of noise, or the spread outedness. How spread out is your model? More technically speaking, variance is your sensitivity to your training data. The idea is, if I give you one set of training data, let's do an example with you guys. Let's take my left-hand side of the room, so you guys right here. Tell me, please raise your hand if your favorite ice cream flavor is chocolate. Only this side of the room. Tell me if your favorite ice cream flavor is chocolate. 1. Thank you. This side of the room. Raise your hand if your favorite flavor of ice cream is chocolate. If I had, see, that was perfect. More than half of this side of the room likes chocolate. Only one of all of you likes chocolate. Now the general question is, how much does my class like ice cream? Or like chocolate ice cream in particular? Now I ask the class as a whole, raise your hand, everyone, if your favorite flavor is ice cream. So please, if the same people raise your hand again. A third of you about like chocolate ice cream. But you see the variance. If I ask one side of the room, I got close to 0%. And if I ask this side of the room, I got over 50%. That has a very high variance because the answer to what is the percentage of people who like chocolate varied, see the word varied, differently versus this side of the room and that side of the room. That's a pretty good example of variance. How changing the data set changes your answer dramatically. Now, bias and variance are very closely linked. That's the thing that we have to be aware of. Because your gut feeling says, well, just lower the bias. That's the best thing you could possibly do, right? Because lowering the bias means getting better predictions, right? I mean, that makes sense. We want better predictions. But the problem is, as you lower bias, your variance tends to increase. Which means your model might be very good at predicting something. Like, for example, if I train my model on this side of the room, it's going to learn that most people don't like chocolate ice cream. That a very small percentage of people have chocolate as their favorite. And I've learned that. But because it's a high variance model, as soon as I take a step back and now ask you guys if you like chocolate as your favorite, and in my mind, I've learned that maybe 4% of you will like chocolate, 1 out of all of you, about 4%. I'm going to be very wrong as soon as I turn to this side of the class. Because this side of the class, 60% of you like chocolate the most. So even though I can learn from you, my model has to be able to generalize well. The whole point of generalizing is I need to be able to be good at predicting even when the data won't come in until tomorrow. I haven't even seen the data yet. My model has to be able to generalize to unseen data. Now, the whole idea about the voters. Can someone explain this graph to me? What am I looking at? What is this graph? Scatter plot of people. The x-axis is how wealthy you are. The y-axis is how religious you are, how devout you claim to be. I guess on some scale. The idea is the red dots are Republicans. The blue dots are Democrats. And the idea was, can we use wealth and religiousness to create a boundary between Democrats and Republicans? The idea being, if, when voting time comes around, which is now, when we start to vote, and someone says, yes, I'm very rich and very devout, your mind will say, ding, 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 you're probably Republican, and I want your vote. So you're going to talk to them about it. That's the idea, anyways. Now, this article uses k nearest neighbors to try to solve that problem. This graph is k on n with one neighbor. And what you're looking at is the following, if it wasn't clear. The light blue means if you're in the light blue region, the closest one neighbor to you is blue. So if you were in this little weird shape, you would be classified as Democrat. Likewise, in this very light red, it means if you're in the very light red, the closest neighbor to you is a red dot. Therefore, you would be classified as a red or as a Republican. This graph actually has a very specific name. Does anybody know what that is? There's a very specific name for this graph that uses a one neighbor to segment out. You want to know? It's called a Voronoi diagram. A Voronoi, V-O-R-O-N-O-I, Voronoi. A Voronoi diagram is actually a very popular diagram when it comes to medical pathology, these essentially diagnosing of diseases, particularly cancer. Many people actually take images and create a Voronoi diagram to segment out the image. And that's what this is called. But really, we know of Voronoi as k neighbors with one neighbor. Same thing. So the idea was, what if we changed k? So right now, we're looking at this data set. Now, if it wasn't clear, this is how the data set is being produced. This dotted line is the model that smart people came up with. That very, very intelligent economists and data scientists and what have you said, this is the best fit curve to separate out Republicans and Democrats versus wealth and religiousness. So take that with a grain of salt, but that's what happened. Anything north of the line is Republican, anything south of the line is Democrat. What they then did was they took all blue and all red and then added noise. So they took a random subset of red and blue and then switched the sides. So you're seeing islands of colors on either side because that's the noise. Because obviously not everybody below the line is Democrat and not everybody above the line is Republican. That's silly. So they added in some noise to make it more realistic. Now with one neighbor, note the red and the blue dark colors. What do the dark colors represent? What did the article say? What does dark mean? Very sure. Super sure. The fact that this is blue is very sure because I'm only looking at the one nearest neighbor. If my one nearest neighbor is blue, I'm going to be blue, end of story. It's 100% accuracy, right? The worst possible scenario is 100% because you're only looking at the closest neighbor. That's why all of them are very dark. As soon as I move K to be 2, look what happens. Now, I could have 100% accuracy if I'm near 2 blue dots, 2 out of 2 blue, or if my 2 closest neighbors are a red and a blue, and now I'm not sure anymore because it's a 50-50 split. So now I either know for sure or I'm unsure. The white is there trying to show you unsure, 50-50. Don't know. Anything between white and very dark is how certain you are. And K and N, how certain you are, which by the way in Sci-kit learn is our predict proba. On our predict proba, as I add more neighbors, I get more granular. Because now I could have a 40-60 split or an 11-89 split. So as I add more neighbors, in fact, I'll increase it to 9, you'll notice some of them are dark still, but a lot of them are fainter red and blue. So this top right corner, which is kind of dark, is probably something like 4 or 5 ninths Republican. Which is why I'm semi-sure it's Republican, but there's doubt. Yes?
Why does white square, white areas when you have an odd shape?
Good question. Honestly, I agree with you. I don't think there should be any white, but I think the way they're calculating it, they might be saying if it's a 4/5, 5/5, 4/9, 5/9 split, I think they're calling that equal. I think that's what's happening because I don't have the code for it. I don't agree with it. But I think that's what's happening. Because there shouldn't be any white. You're right.
And why do I get a slightly different figure on my computer?
Because if I click this button, I can generate new training data. It's all random. As I increase K, notice what's happening.
It gets more certain about who's who.
It's getting very uncertain. I'm now at 64 neighbors. Very uncertain.
That's overlapping it.
Actually, quite the opposite. It starts to not overlap. Because these white dots in the middle are just very unsure. Because I have 96 neighbors to compare, it's much more likely to be very unsure. So with 96 neighbors, I'll go ahead and make it an even 100. If I have a 48 split, 48-52 split, that's a very unsure. Sure one wins, but not by much. So these whites are trying to show you where it's pretty unsure of what it's supposed to be. Does it make sense, the following statement? When there was one neighbor, there is no white, because if you're only comparing yourself to the closest person, you always have a 100% chance of knowing what you are. If I only compare myself to you, and only you, there's no room to be wrong, because you're the only person I'm listening to. Here's an example. Is Titanic a good movie? Yes or no?
I think so.
Yes. Is Titanic a good movie? Oh, hold on, sorry, before you answer that. Yes, if I have a one neighbor classifier, I now believe Titanic is a good movie. Is Titanic a good movie? I now have a 50-50 split between my friends. I don't know if I should watch Titanic. Is Titanic a good movie? No. Now is it actually stronger no than yes? That's the idea. As I add more K and neighbors, I'm increasingly becoming unsure of what to do with my life. I don't think it's a good look at. Sorry. Why did you lie?
Because I thought it would make it interesting.
Well, now you told us you lied, and okay, fair enough. She lied, everybody.
It's a lie, I'm a liar.
She lied. She's a liar.
I like Titanic.
Fine. Okay. Doesn't matter. Thank you, though. So, but does it make sense that when I ask one person, I only have one opinion, I'm very sure. If I ask 21 people around me, I'm much more likely to get stuck in the middle. Now, can someone explain this graph in terms of bias and variance? It's actually written on the screen right now. Explain the movement of K in terms of bias and variance. You can repeat the sentence on the board that is the relevant statement to describe what's happening to bias and variance as K goes up and down. I'm allowing you to read it verbatim. Yes?
So when K is low, variance is high.
When K is what?
K is low,
When K is low, okay.
variance is high, and bias is low.
Why? Explain that first. So you're saying when K is low, you have a high variance and a low bias. So here's a very low, here's the lowest K, 1.
So I'm saying this high variance because if you move a little gap, it will change colors.
That's a very good point. So you see these islands, and if I give a different training set, it might be a little bit more. See these islands of red amongst the blue? If you see something like that, that's a very good example of a high variance. It means if you move a little bit in one direction, you have a very good chance of changing your answer entirely. This button down here called Generate New Training Data also helps explain it. Generate New Training Data is actually taking different noise. Now notice, as I change the training data, look how drastically my predictions are changing. My predictions are changing drastically with every click of that button. Those islands are moving around a lot. Now with the highest I can look at, 100 neighbors. So that's the opposite. This is a low variance, high bias. High bias because look how often I don't even predict anything. I'm wrong a lot. Because look how those that aren't even getting predicted because it's not strong enough. It's a high bias because I classify very few people. In here, I classify everybody. Everybody gets a turn. But at 100, high bias. A lot of wrong. But low variance. Which means, watch what happens when I keep clicking Generate Training Data. It's changing, but not as much as it did when there was one neighbor. You still have this kind of darkish blue blob at the bottom, this kind of red blob at top, and it moves from like left to right a little bit, but it really doesn't change that much. Not as much as with one neighbor. When I change the noise, the one neighbor changes drastically. And what I'm doing right now with the changing with one neighbor is like asking this side of the room if you like chocolate and then that side of the room if you like chocolate. I change my training set, my model changes entirely. If I learn from you, 4% of the population likes chocolate. If I learn from you, did you lie about that? Don't lie to me. Did you lie about that one too? Good. Okay. Fine. If I learn from you, 4% of the population likes chocolate. If I learn from you, 60% of the population likes chocolate. That's a very high variance model. Very high variance because it changed dramatically when I changed my data set. As I am here, as I change my data set, my predictions change wildly. Whereas with 100 neighbors, if I change the data set, I'm still pretty much predicting the bottom as blue and the top as red. And sure, yeah, I'm getting different answers for a little bit, but it's not drastic. I'm not seeing, notice, there are 0 islands anymore. There's such a low variance that there's 0 islands. This concept is very difficult to digest, and it will be brought up several times in this course. Every time I introduce a new model, I will talk about the bias and the variance of that model. Yes?
So if you had a perfect model with the variance and bias also be low.
Would in a perfect model, would the variance and bias be low? Yes. And also in this same world, Donald Trump, I'm not going to say it. You know what? I apologize to anyone. Last class, I made a lot of jokes about Justin Bieber, and then I got off on a tangent. In the same perfect world where a model would have low bias and low variance, my pet dog, my pit bull, is also speaking English, has a horn coming out of the top of its head, and is a unicorn. Does that make sense? It doesn't exist. Yeah, pretty much, unfortunately, if there was a model that existed that had a low bias and low variance, you all just wasted your money on this class because all I'd have to do is teach that model and we'd be done. Unfortunately, that model does not exist, and what we learn is a variety of models which have a very different combination of bias and variance. For example, towards the beginning of the class, we will be focusing on models that are higher bias, lower variance. Now here's a pop quiz. I just said the term, or the phrase, higher bias, lower variance. Someone describe to me what I mean when I say the models will be of higher bias. What does that mean in layman's terms? Explain it to your mom. Honey, I don't know what that graph is. Your mom. It's a higher bias. What does that mean? Tell me what it means.
This is very high level, but the model is more short, like more fine-tuned to the opposite. Okay, less sure.
Less sure. If it's a higher bias, it's wrong more often. That's pretty much the easiest way to say it.
But it thinks it's more sure.
No, it doesn't. No, it tells me it's not sure. Our metrics will tell us that. Our accuracy will tell us that. A higher bias will tend to have more error, as in a lower accuracy, for example. Higher bias means wrong. You guys want to explain it? Is there a better way that you guys have heard, Matt, David, Sri, any? For bias, higher bias? How would you describe high bias? A little louder, I can't hear you. Right. I can't hear you at all.
Sorry. Both of those will give you a sense about whether you're overfitting or underfitting data.
Sure.
And something that's high bias is going to be much more stuck on certain pieces. As opposed to high variance, might not be able to generalize.
Right. So when I say lower variance then, what does that mean? Lower variance, this is the harder one.
That there are fewer points that are uncertain.
That say it again?
That there are fewer points that are uncertain.
Close, you're on the right track. And this is definitely the harder one to explain. Do you think you can explain what's lower variance mean? Reproducible, I'll use another word for that, generalizable. So a lower variance model generally means, if it's lower variance, it means it's not as wacky. It's not as wild. It doesn't move all over the place if I change one little subset. It would be like if I asked this side of the room 55%, that side of the room 60%, okay, pretty close. I changed the data set, but it's still pretty much 55 and 60, probably 57% of the world likes chocolate, yeah. Yeah, so we're going to get to those terms. Under and overfitting are the ways to describe that. But yeah, but bias and variance by themselves also have meaning. So a low variance, high bias, means that the model doesn't tend to change too often. It's predictable. But high bias means it's not really hitting the nail on the head. Perfect example, I love these targets. I love these targets. Low bias, high variance. I'm sorry. what I just said. Low variance, high bias at the bottom left. Low variance means I keep hitting pretty much the same place. The high bias part is it's not the target. Yeah.
So our accuracy and precision kind of pretty much good proxies for bias and variance. Because if you're highly accurate, not very precise, you'd be low bias, high variance, right?
Correct. And these terms, precision, sensitivity, specificity, if you've heard these terms before, they will become a big part of the course later on, but you're correct. Different metrics will tell you different things about your model. So accuracy by itself isn't a great way to determine both bias and variance. We have other metrics for that, and we'll learn probably a total of 20 metrics in this class. You've learned one today, accuracy. Yes?
So if we talk about generalizations, you have an answer that is generalizable. You say that there's like a normal distribution, and that generalizable, that's the mean. The variance is the distance, the possible distance from that mean you get from running your model.
Fair enough, but to make it more precise, it's distance squared. If you want to put it more mathematical. Idea is, you have some distribution. And the middle is what you're expecting, your mean. And then your variance is, well, if data exists over here, over there, over here, over here, at various distances away from the mean, it's very high variance. Top right, high variance, low bias. Every time I throw this arrow, I get pretty close to my red target. But every time I throw the arrow, it's probably pretty far from the last place I threw the arrow. Your best thing is up here. It's that unicorn model. The low bias, low variance model. Doesn't really exist, quote unquote. There is no model that is the catch-all, end-all, low bias, low variance. However, for certain problems and certain models, you can achieve this. This is achievable. It's not something like you've never even heard of it. It's achievable, but you cannot always achieve it with one particular model. Which is why we have to learn several different models, because each of them apply to different situations better than the others. Okay, bias, variance. Complicated concepts, I know. We're going to keep coming back to them over the class. Next, I want to show you here. This managing part, I'm going to kind of breeze through this because you read it, you should read it again. This is super important. Fight your instincts. For the love of God, fight your instincts. A gut feeling many people have is that they should minimize bias at the expense of variance. What happens when you do that? Remember, minimizing bias means you're right more often than not. But at the expense of variance, what does that mean? What would now happen? If you have a high variance, low bias. Let's say, again, I'll take a different example this time. Fine. Not the ice cream example. If I have a low bias, high variance, let's say I am a political analyst and I want to conclude that young people are Democrats. I would like that to be the case. Fine, fair enough. Okay. I'm going to ask 25 people who are under the age of 25 if they're Democrats or Republicans. And I get that about 70% are Democrats, 30 are Republican. That's pretty good. I'm not satisfied. I asked 25 more random people under the age of 25. Now, 98% of them are Democrat, and then 2% are Republican. That doesn't make sense. 96 and 4%. So one person of the 25 was a Republican. This random sample seems to conclude that 96% of people under the age of 25 are Democrats. That's me minimizing bias at the expense of variance. I no longer care if my model, me asking people, is going to generalize to all under 25-year-olds because I've chosen a specific subset of data that supports what I want. And welcome to the world of academia. I mean, kind of. Does that make sense? That last example, because I've never said that example before. And I want to see if that actually makes total sense. I'm getting some blank looks. That's chill. Yeah.
Can you explain how that's low bias?
Yes, because it's low bias because I've now fit my model, which is that 96% of people, I can now accurately predict if someone under 25 is a Democrat by saying 96% chance. I'll say the whole thing again and with a little bit more data to see if that helps. I have 25 people under 25. Are you Democrat or Republican? 96% of them say Democrat. My model is now the following. If you are under 25 years old, you have a 96% chance of being a Democrat. That's now my model. I have trained on those people, and I am now trying to generalize it outside of those 25 people. Does that make sense so far? The model is me just regurgitating 96% because that's what they were. This small subset over here. That's my model. My model is just me saying 96%.
It's a little biased for that sample of data.
Yes.
I feel like it could be wrong. Like, from general.
That's the high variance part. The high variance part is, as soon as I leave this subset of people and ask other people under the age of 25, I'm going to find that it's not 96%. It's going to be a lot lower. It did not generalize well outside of this small sample of data. Yes?
So in the example here, it says using a phone book is an example of a source of bias.
Okay.
As in you pick that versus maybe a internet mailing list. Like, and say that one demographic was wealthier than the other. A phone book, people who were poor, and the mailing list, they were rich. So isn't it biased to select one list over the other? It seems like you were selecting one group of 25 over the other. How is that?
Biased means something different in terms of, you're biasing yourself towards a variable. In this case, bias does not directly mean what you just said it was. Because when you say, oh, that's a very biased opinion, that's a different type of bias that I'm talking about. When you pick only the phone book, that's saying, oh, I'm confining myself to this sample. Now, it's similar in the sense that, so let's generalize and say people who are in the phone book are less wealthy, people on the mailing list are more wealthy. If I only survey the people in the phone book, you could say I'm biasing myself towards the phone book. And therefore, I'm going to be decreasing my bias. This is why the words get confusing. I'm decreasing my bias because I'm learning really well what the people in the phone book say. But as soon as I leave the phone book people and try it somewhere else, it's not going to work. So the low bias means that I am fitting myself very well over here in the phone book. But as soon as I leave the phone book, I'm not doing so well. I have a high variance now because my model is not generalizing well outside of the phone book. So low bias means being right no matter what. No matter what. Question?
Well, I was just going to mention, so it is called sampling bias, and it's actually something that when you collect data, like I've been on that side of things, like there are various tests of sampling bias, and there's lots of ways to fix it, but what I got from the article is that mathematical bias is a very different thing than like collectors.
It's a different word. They are related.
Right.
They are related, but mathematical bias and like sampling bias in statistics are different terms, which is why it can be confusing. Variance is even a different term, as you know in statistics. They are related in the sense that when I say variance in terms of machine learning, it is a type of statistical variance, but it has a different connotation. When I say high variance, what I'm trying to say connotationally is this model doesn't generalize well. If I say it's a low variance, I'm saying it generalizes better than the high variance model.
And the question though that I have is that, are there like better ways, is it easier to fix bias than to fix variance? Because I feel like in sampling there is also, the other type of bias and variance, it's easier to correct bias that way for people.
It's much easier to correct bias.
Okay.
Much easier.
Same thing mathematically.
If you think about it in non-mathematically even, if I want to be right more, ask the right people. If I want to generalize more, I have to ask a lot more people and have better data, which is just harder to do in general. It's much easier to correct your bias. Which is why, in data science, we generally start with a high bias model. with a low variance, because low variance is hard to achieve. We start with a model that tends to be low variance, high bias, and then try to get the bias down. So we start with a model that already has a low variance, which is difficult to achieve, and then we try to bring down the bias by adding better features or removing irrelevant features and doing all this data manipulation. All right, overfitting and underfitting. What you're looking at here is a very, very common graph. What this graph is telling you is the following. The x-axis is model complexity, which essentially means how weird is your model? How much room, how much wiggle room does it have? For example, if I want to determine whether or not you're Democrat or Republican, and I only choose one variable, your age, that's not a complex model. It's over here on the left-hand side. Not complex. I just have to ask you one question, how old are you? And I have my answer. As I add more variables, what's your average income? Are you married? Did you go to college? Do you have a PhD? Do you go to church every Sunday? As I keep asking more things, I'm moving to the right on the graph. I'm adding complexity to my model. I'm giving you more wiggle room. Because you could be a young person, 19 years old, but goes to church twice a week. You have these different ways, clusters that you can be in. So I'm adding complexity by asking you different questions. The y-axis is my error. Is how often I'm just wrong in my model. So a low error means that my model is very accurate. A high error, it's up here, means that my model is getting a lot of things wrong. Now at the left bottom, so not complex model, excuse me, if my model is not very complex, I get a lot of error. Which makes sense. If I only ask you one question, how old are you? I'm going to get this question wrong a lot. Like I asked these guys, how old were you? Oh, 96% of people under 25 are Democrats. Done. Are you younger than 25? Yep, probably a Democrat. Moving on. You're going to get wrong answers a lot. So lower complexity models tend to have a higher error. As I move towards the right, if I'm asking more and better questions, how old are you? How much do you make? Do you own your own business? As I ask you more questions, I'm getting more to the root of are you a Democrat or Republican? Therefore, my model is getting better, my error is going down. At a certain point, you reach what's called the optimum model complexity. The optimal model complexity is the point at which your model is just complex enough that you understand the problem. Here's the problem. Your gut feeling will say, well, if I ask more questions, I can get even more granular. As you add more complexity, what tends to happen is, sure, you're getting more granular, but these islands start to form. You're getting so granular that you're seeing that, oh, well, this area is generally blue, except for this really, really weird subcase of people who are Republicans in this area. So you're creating these islands by adding complexity. Go back. And what generally happens is, after your optimum model complexity, if you add more questions, more predictors, your error shoots back up. So it's all about finding this dotted line, the optimum model complexity. Just complex enough that you understand the problem, but not too much that you are overcomplicating it or overfitting, and not enough complexity so that you're under fitting the data. So underfitting on the left, and as you move to the right, you hit your optimal model complexity, and as you go more towards the right, you're overfitting your data. You are learning almost too much about your model. You're getting too nitpicky. As you get very nitpicky, you tend to overfit. Overfit basically means you are learning to one subset only, and you cannot generalize out of it. No, I'm going to get to your question in a second. On the left, I have low variance and a high bias, which means my model is very stable, but I'm consistently wrong. As I add complexity, I'm actually reducing my bias because I'm getting very granular. I'm finding these really weird islands of Republicans among a sea of Democrats. And it's like, wow, these young people who don't go to church, who are, who are atheists, who have all of these generally democratic principles, are Republican because their parents are divorced. Like, you're getting to these really weird reasons for why people are Republicans and Democrats. And the problem with that is, as you're adding that complexity, your bias is going down, which in a way is good because you're learning more. You're learning, oh, weird. Divorcing parents tends to be I'm making this up, tends to be a predictor of Republicanism. That's so strange, because it is. Because what happens as you add complexity is your variance shoots up. Now you have this idea in your head that people with divorced parents are Republicans. So now when the next person comes in with divorced parents, oh, I've seen this very, very strange example before, you're a Republican. And they say, no, why would you assume that because my parents are divorced? That doesn't make sense. You see how it can be very tricky. As I add complexity, you could argue I'm learning all of those granular cases, but now I've nitpicked my way to a really good accuracy, but now I can't generalize. I don't really understand the core problem. I only understand really weird subcases. Yes. Sorry. Oh my God. Patrick. Sorry, Patrick.
Is it fair to think about it that you have a training data set and low bias is minimizing error on that training data set, whereas variance you think about it in terms of adding outside data?
Yes. Perfect. I'll say it again, too. Reducing bias is all about fitting yourself to the training data. As soon as you have out-of-sample data, which is data you have not seen before, if you cannot generalize well, that means you have a high variance. And that is overfitting. Overfitting, over here on this side, is when you fit really well to your training set, but you cannot generalize. On the left, we have underfitting. Your model is very stable, but you're wrong a lot. I've underfit. I don't know enough about this model yet. Here's the sweet spot. And we're going to learn how to find that sweet spot. Question? So?
Yeah, Brett.
Brett, sorry. I knew that one too. I didn't even say it.
This might be a little ahead of what we're talking about
Okay.
now, but I'm wondering how bias towards anomalous events, anomalous data points, is that that happens? Or that is included in some models, right?
And that's what bias means.
So I'm from I'm from Oklahoma, and everybody I know goes to church, and then everybody I know who goes to church votes Republican. Then I meet one person that also votes Republican. So I believe that every single person, or maybe that's a bad example, but I have one brand new data point,
Okay.
and I make a massive generalization about every single person who has that data point that goes against my prior model.
That's more about variance. So what he's saying is, if I have this idea, this model, and then one more data point gets added in, which drastically changes my perception, or my model, that's an indicator of high variance. And we're going to see that in code in just a second. If your model is sensitive to the data that you're using, that means it's a high variance. If it changes drastically because that one person came into church who votes Democrat, it's a high variance. One more question, I have to move on.
Example of this was later in the class, we're going to be looking at the tag set on tenant, right? So, whether or not people survive.
Yeah.
You can perfectly train the set on saying, I know that everyone in this list by name, and I know them by name, and I know if they live or not. As soon as you introduce someone out of that set, you no longer think that name.
Mhm.
It would be
It's like if I asked you, so what he was saying was, if you learned the names of everybody who died on the Titanic, you would be able to predict perfectly who died on the Titanic if you all knew them by name. But as soon as I give you a fictional person that has some attributes, you would not be able to tell me their percent chance of survival because all you've done is memorize the names and if they died or not. Here's another example like in school. If I ask you the same question over and over again about, let's say, wars, like wars. Let's say I ask you, okay, at one point in history, people in America fought people in Britain and they won. That's the Revolutionary War. And we won. And he's like, yeah, it's awesome, go America. And then I say, well, guess what? In 1812, we fought again. Guess who won? And you're like, America. And no, because we lost the war of 1812 very terribly. Read a book. If you don't know what I'm talking about. They burned the White House down, which is why it's white. It used to be gray. Fun fact. Okay. But that's the thing. You could memorize that America always beats Britain. And then as soon as I give you another scenario, oh yeah, and then we fought again in the 19th century, you're inclined to say, oh yeah, and then we won that one too, because America always beats Britain. But that's not true. You've learned a very specific thing, but you did not learn to generalize outside of that thing. You've learned that Americans generally tend to win wars, and then when I give you a war that America was in, Korea, you say, yeah, we totally won Korea. Also read a book. I'm not answering that question. That was a weird example. I don't know if that worked, and I apologize. I'm going to watch it later to see if it makes sense. That's all I'm going to say about this article, and I'm going to move on to the code based on this article. So the bias and variance.py file, 06 bias variance, is about training a model that will predict the weight of a mammalian brain as correlated to their total body weight. So the idea is, would an elephant have a bigger brain than a human because an elephant has more mass? That's the question that we're going to try to answer. So I'm going to import a couple things. Pandas, NumPy, and Seaborn. Pandas for data manipulation. NumPy for math. And Seaborn as a really nice graphing tool. This data set comes from Florida State University, if I'm not mistaken. Florida State University did a study where they took 62 mammals and then they plotted their average brain weight and body weight. Sorry, take that back. Brain mass and body mass. So if I read the table in, here's the head. So for each animal, I have a brain weight and a body weight. And you can see the brain is generally much lighter than the body, which makes sense. I can do a quick describe of my data frame, and I'll get that the average brain mass is 198. And this is kilograms. And body, wait, I'm sorry, I misspoke. There are different, oh sorry, this is grams. Brain is in grams, body is in kilograms. Yes, yes. Body's in kilograms, brain is in grams. Does it matter that they're not the same unit? Technically, you should be asking questions about that, but the fact that kilograms is off by 1,000, a factor of 1,000, makes it fine. It'll just scale, it'll look differently, but the relationship won't change. So, I'm going to focus where the body weight is less than 200. Just to kind of make it smaller, to make our plots a little bit nicer. So on line 21, I'm just filtering out my data frame such that the data frame body mass is less than 200. So when you look at our shape, and we have 51 animals, and there's 2 columns, brain and body. So we're going to pretend for a second that there are only 51 mammals in the world. So this entire data set is for every known mammal species. That is our assumption right now. that we have a lot of mammal data, and there's only 51 mammals in the world. Here is a basic scatter plot to show body versus brain mass. So as you can see, as the body weight gets smaller, the brain weight is also smaller, and as you move towards the right body, you see this kind of upwards trend. And we're going to try to model that trend. And you used Seaborn before, the day I wasn't here, correct? You guys used Seaborn before, so this is familiar. If this was not installed, please raise your hand and let us know. But not installed? Seaborn?
It has issues.
Issues?
It says no module.
You need to install it. If you do not have it installed, please write the following command into your terminal. It's on the GitHub. Where'd it go? Here it is. Our Conda, can we do Conda install Seaborn? Conda is now so just do Conda install Seaborn. Yes, Conda install Seaborn if you do not have Seaborn installed. Is it working? Yes? Excellent. There seems to be a relationship. That much is obvious. Let's try to make a prediction. I'm going to make a line of best fit. And I know we haven't learned linear regressions yet, but bear with me. I'm going to draw a line that pretty much goes through my data points. It looks like this. This line goes through my data points. The whole point of the line is I'm going to use it to predict. So if an animal comes in with body weight 150, I would look at the line and say the brain is probably around 60 by looking at the line graph. With me so far? Excellent. So we drew this line, but here's where the bias and variance come into play. I'm going to now, of the 51 mammals in the world, I'm going to take a random subset, 1 and 2, half and half. I'm going to take a random subset between them. And as I mentioned on the NumPy day on Monday, I can make numbers not random at will, because I know how random numbers work. I'm going to set my np.random.seed to be 1, 2, 3, 4, 5. Why 1, 2, 3, 4, 5? I made it up. But if we all do 1, 2, 3, 4, 5, we will all get the same exact random numbers. Because random numbers, as you learned on Monday, are not random at all. It's just a series of mathematical functions performed to the current date time on the computer. So if we all start from the same number, we'll all get the same random numbers. Why am I doing this? So that it's easier to explain the following. When I look at the head, we should all see the same sample of 1, 2, 2, 2, 1 on the first 5 rows. So for every mammal, I've randomly assigned it to either sample 1 or sample 2. So far, so good? I have a bunch of mammals in sample 1. It's like, here's a bunch of 25-year-olds over here, and another bunch of 25-year-olds over here. Or, here's this half of the class, and here's that half of the class. I'm going to have this half of the mammals and that half of the mammals. Now I'm going to make 2 plots. One of them is going to plot sample 1's mammals. The other will plot sample 2. And for each one, it's going to draw a line. This looks really similar, and for a reason. Look really closely, you'll tell they are actually different. You see there's only 1 dot up here, and here we have 2 dots. These are actually completely different data sets. There is no point that belongs to both graphs. And yet, what can you tell me about the line between both of them? They're pretty much the same, aren't they? I can hardly tell the difference between them. This is even more clear in the next set of code where I put them both in the same graph. Sample 1 is taken by the blue line, and sample 2 is the green line. They're pretty much the same line. Now, I'm going to ask you a question. This line, If I used it to predict, like the actual predict the brain weight versus the body weight, would it be right a lot of the time? I'm getting a lot of no's. Why no? Here's an example. Let's use this green line like it matters. Let's say I have a body weight of 150. What would my line predict? About 50. But if you look at the animals that are actually 150, there's 100, 160, and 200. This line doesn't do a very good job at predicting these points up here. Does this have a high bias or a low bias? This is tricky. Hold on, think about it for a second. All right, let's try this. Think about it, take 20 seconds. Does this have a high bias or a low bias? Don't say it out loud. Think about it. High bias, low bias. Okay, raise your hand if you think it's high bias. Raise your hand if you think it's low bias. Raise your hand if you're still totally not sure. Fair enough, thank you. For those of you who said high bias, why? What does high bias mean? So why did you choose high bias?
It's wrong a lot, even on its own.
It's wrong a lot. TAs, what do you think? High bias, low bias? This line, this linear regression. High bias, low bias. I'm keeping you on your toes too. That's, yeah. Keeping you guys on your toes. That is totally a high bias model. Because, nail on the head, it's wrong a lot. It's wrong a lot of the time. And by a lot. If I guess this 100, I'm sorry to call you, I didn't mean to. At 175 body weight, the line would put me here. But look where they actually are. It's wrong a lot of the time. That means high bias. Is it low variance? And I'll answer that for you. Yes, it's low variance, and this is the trickier one. It's low variance because even when I chose two totally different and random data sets, the lines still ended up being pretty much the same. The model did not change much, even when I totally changed the sample. That means the line is generalizing well, even if it's wrong sometimes, more often than not, honestly. This is a low variance, high bias. A lot of wrongness, but very stable. Very stable. Does that make sense? A little bit more sense? Totally different data sets, but the lines still ended up the same. What's the point? Well, what if I tried adding model complexity? Because right now, back to that article, to this graph, right here, the linear model is a very non-complex model. Not complex. Which means that a high bias, look at that, the red line, and then here, low variance. High bias was wrong a lot. Low variance, it was stable. Now I'm going to add a lot of complexity. I'm going to give it a lot of free rein to try to lower that bias. Down here, in line 101 to 104, I'm going to ask the same thing to do the two samples and make two different models. But instead of asking it to draw a line, I'm going to ask it to draw a polynomial of 8 degrees. Now, someone tell me, what does a polynomial of 8 degrees have that a line cannot do? What can a polynomial of 8 degrees do that a line cannot do? It can go up and down. How many times? 8. The number of degrees in a polynomial means it's allowed to go up and down up to 8 times, up to. It can do less. I'm going to ask it to fit the same sample, samples 1 and 2. I haven't changed that. But instead of a line, make it an 8-degree polynomial, and this is what happens. Are these curves similar? Not in the slightest. What happened was, when I gave the model free rein, Look at the first graph. It's going up, it's, oh, there's some points over here, it's going to come down, it's going to go up, it's going to go down, oh my god, look at this guy, and come back down. Because it's allowed to. It's allowed to do all these twists and turns. This is the part where I ask you 8 really weird questions to try to figure out the nitpicky parts of are you Republican or Democrat. Over here, I get to do the same 8 things, but because the data's different, it goes, oh, I start here, up here, down here, way off the graph, down here, then off the graph again. I told the models they're allowed to do the same thing. Ask 8 questions, or move up and down 8 times, in other words. And for each different sample, it did something totally different. This has a low bias, which is that thing that you think is all great. It has a low bias because look how good this curve is. Look how amazing this curve is. It's so good at hitting all of these points, and you cannot argue with me. This curve does a very good job at getting close to those points. But what if I took different points from the same population and tried it again? Look how good this curve is. This curve is so good at hitting these points. The fact that these curves are so good at each individual sample, but not similar to each other, means it's a high variance model. Back to our curve here, we've entered this part of the graph on the very right-hand side. I added a lot of complexity, and my bias went down. My curve became very good at hitting those points, but it's very susceptible to new points. If I added a new point, it can start here and go, oh, I want to get that point, and it can shoot back up to get it. This concept is very difficult, I'm aware, and this is why I'll be bringing this concept up throughout the remainder of the course. Sorry, just before. Let's try something in the middle. 1 was too low bias, 8 was too high variance. Here is order 2, i.e. quadratic. This, I would argue, is a very nice sweet spot. Sure, the curves are a little different, but not by much. It still generally starts down here and then curves upwards towards the end. Is it a good bias? It's not great. It's wrong, it's a decent amount. Is it as wrong as the linear? Definitely not. It's much better at predicting than the linear model. So here's how you should think about this. This graph right here, the quadratic one that I'm pointing at, generally predicts better than the linear model, but it has a lower variance than the 8-degree polynomial. This is a sweet spot. By looking, it's pretty obvious. But in general, we won't be able to look at these graphs to figure this out. Which is why in the next code base, we're going to be using Sci-kit learn and the metrics available to us to figure this out without graphs. But before I do that, and in fact, before I do that, are there any questions about this? Yes?
So if you look at this graph, I think it tends to very low bias towards the lower side of the body weight, and then as the body weight increases, it seems to be a little bit more.
Yeah, so you can argue.
Sorry.
Sure. So you can argue that the graph does a better job on the left-hand side. It's much closer to these points than it is over here. And that is correct, and it's very good to note. But when I talk about bias, I mean bias as a whole. So in general, how good is it? You can break it down and say it's better over here than it is over here, or whatever it is. But in general, the bias looks at all the points. But it is good to know that the curve does better on the left-hand side than it does on the right-hand side.
So there will be a situation where you look at the data and say, okay, at this point, this body weight is this model, and let's say this body weight.
So the question is, if question is, if I understand correctly, let me know. At what point do I say, okay, maybe I should cut it off and say, well, if the body weight is less than 50, here's this model, and if it's greater than 50, here's another model. That is a correct way to think about it, and it's more of an advanced way to split it up. It's more of a data scientist job, not the model's job, but you could do that. You could say, this is my model for when it's less than 50, this is my model for when it's greater than 50. And that is possible, yes. That is a common technique. Any other questions about bias and variance in this data set? Okay. Well, let's talk about how to optimize. I'm going to go to the slide deck. It is in the slides folder. Model evaluation procedures. So this is how we do what we just did, not graphically, with numbers. So suppose we train our model using the entire data set, like we did in KNN. How low can we push the training error? And the answer is down to 0. Like you just said, you can memorize it. If you keep comparing the flowers to itself, you'll never be wrong. If I give you a test that was the same as the practice test, you can't get it. Well, you could. But you could get everything right just because you memorized the practice test. That's what's wrong with training error. That's overfitting. This is the definition of overfitting, is memorizing our training set. Here's an example. This black curve, the black curve is a line that is, or curve, that is trying to separate blue from red. It is underfitting in the sense that it's wrong sometimes. There are red dots over the black line, there are blue dots under the black line, and it's getting wrong sometimes. The green line has a very low bias and high variance, and it's overfitting. It's overfitting. The green line, put it this way, the green line is trying too hard to put everything on one side and everything else on the other. It's trying too hard. Because the problem with the green line is, as soon as I add a point, it's very likely to get it wrong, and the green line says, oh, let me just push this line just a little bit to make sure that it's the right thing, and it's going to nitpick. It's nitpicking again. The black line doesn't know enough. The green line is nitpicking. Similar to what we just looked at, the same data points with a linear model versus a model of degree, it looks like about 10. The line on the left is underfitting because it's not doing enough to try to touch those data points. The model on the right is trying very hard to touch those data points. It's going up and down, just to get it as close to perfect as it can. The problem is, it missed the point entirely. It nitpicks so much, it doesn't get the gist of the problem. To put it in another way, look at X versus Y. It doesn't even matter what they are. What does the line understand that this curve does not understand? So while this curve is very right, what is this curve missing? And this is more of an intuition question, not math. What is this curve missing that the line understands? Yeah. How they're correlated. That's exactly right. What the line understands is that as X goes up, Y tends to go up. That seems pretty basic, but this curve missed that fact entirely. Because you know what this curve understands? It goes up, and then it gets to this point, it goes down, and then it gets to this point, it goes up, then it gets to this point, and it goes down. It doesn't get the general idea that as X goes up, Y goes up. It doesn't understand that. Because it nitpicked too hard, it overfit itself. It missed the point. So even though the line is wrong more, it has a better understanding of the situation as a whole. Training error is not a good estimate of accuracy beyond training data. Beyond training data means the data that hasn't been born yet. I mean, in the terms of neonatal infection, literally the data that hasn't been born yet. Training data beyond, data beyond training data means the unseen data that no one has seen yet. Why this matters? The prediction that we're given, the data that we're given for prediction is not the end of the data stream. Example, if a new UFO sighting comes in, if new UFO sightings come in, new irises will be discovered, new children will be born, all of these things. Tonight, there are UFOs reported every day, literally every day. But I haven't looked at them yet, because they haven't happened yet. So the data that I fit to my model does not know about the UFO sightings tomorrow. This is the data that I'm talking about when I say beyond the training data. Because data didn't just stop when you told it to. Stock prices change, UFO sightings come in, children are born, yes. Sorry? Absolutely not. The question was, does that make Titanic less interesting? No. Because you know what? Boats are made every day. And big boats, the biggest boat in the world, is made almost every year now. So the Titanic, sure, at the time we had less technology, if you want to think about it that way. But at the time, the Titanic was the monolith of ships. It was literally the unsinkable ship. We say that today, and we're still wrong about it. We're still wrong about things that are unbreakable. We are. We think this building will never fall down. And then, at one point someone forgets to put the concrete in the steel and it collapses. We're still wrong about that. Does that make looking at Titanic less interesting? Incorrect. I think Titanic is just as interesting. So how do we build a model that generalizes? Because obviously, we haven't seen the unseen data yet. Think of it this way. Here's a rectangle. This is our data. All of our data. So all 150 irises. All 20,000 UFO sightings. All whatever. All of them. And here's my model. It's the white box, not the black box. We know what's going on inside. It's not a black box. Split it up. Split up our data set. Make like 70% on one side, 30% on the other. Take the top part, call it your training set, and train your model. The bottom half, which we haven't touched yet, call that the test. So train your model on 70% of your data, and then test it on the remaining 30%. Why? Because if you do this, we're pretending that this test set never existed. We're pretending that we haven't seen it before. And we're training our model on only a part of our data set and then testing it on the rest. Yes? Good question. Aren't we biasing ourselves because we're choosing a specific 30%? Yes, if you only do it once. And there's something called cross-validation where you do it several times. And we're going to get to that today. Then you tune your parameters, maybe 1 neighbor versus 7 neighbors versus 4 neighbors versus 80 neighbors. And then you choose the best one. That is the general idea. Split up the data set, train it on one part, test it on the other, tune your model, make it a little bit better, and then choose the best one. And then when you're done, train it on everything. And then when tomorrow's new data comes in, you're ready. There's my new, it's orange. There's my new data. This new data, orange, is called out-of-sample data. Out-of-sample data is data that you haven't seen before, at all. Like it hasn't happened yet, essentially. We want to estimate how well our model will do on this out-of-sample error. And we do it using this method. This method provides a good way of estimating how well we would do on unseen data. Now, to your point, how well does it predict out-of-sample error? Not so well. Because what if we chose a different sample, to your point, right? What if we chose a different 30% to test it on? And our model was of high variance. Wouldn't that be bad? And yeah, it would. Which is why we do something called cross-validation. Cross-validation is the idea where we do this training test split many times. Here's what it looks like. It's called k-fold cross-validation. And guys, I'm aware that today is kind of terminology heavy and theory heavy, not so much lab heavy. In fact, there's no lab. But this is really crucial stuff, and it's going to become basic knowledge to us by next week. This is what we're going to be like baselining our conversation on. Is, okay, this model is a high bias, what do we do? We're going to do cross-validation. Got it. This is going to become very second nature to you. Here's how cross-validation works. Randomly split the data set into k equal parts. So if k is 5, different k than k nearest neighbors. Choose k to be 5, we split the data up into 5 equal parts. Step 2, take 1/5 of it, one of those 5, set it aside. It's over here. The remaining 4/5, train your model, and then when it's ready, test it on this 1/5. So far it's no different than what I just talked about. But then the next step, take that 1/5 I just tested on, put it back, take the next 1/5. Train, test. Put it back, take the next 1/5. Train, test. Put it back, take the next 1/5. Train, test. Put it back, take the last 1/5. Train, test. What that does is, every single point has now become a member of the test set at least once and a member of the training set at least once. So not only are we randomly assigning them to partitions, we're actually performing the machine learning k times and then averaging the results. And for a model with high variance, this is the best way to minimize, or rather, to estimate the out-of-sample accuracy. Cross-validation is the best way to estimate out-of-sample accuracy for our models. Essentially, we're going to do our models several times on several different data sets and then average them all together. Does that make models less variance? No. But it does account for how it will behave in the wild. It doesn't make our models better. This does not make our models better. The model tuning, the parameter tuning, changing k from 1 to 7, that makes it better. This is just estimating what it's going to do when I set it loose in the wild tomorrow. This is fun, isn't it? Are you saying yes, this is fun? Oh, okay.
The K is the length of the data set, right? If you do that essentially as long as it is, wouldn't you be super overfitting the model?
Sure, which is why you don't do that. Which is why in general people choose between 5 and 10 as a good K for cross-validation. I generally do 10 different splits, and I do the model 10 times. Here's an example. Same data set on all 5 graphs, but in each one, I choose a different K partition. So in every graph, the red is my training, the blue is my test. Note in every graph, the blue changes. So look at this dot on the bottom left, the very bottom left on your slides. It's blue in the first graph, correct? Note in every other graph, it's not. Every data point belongs to the test set once and only once. And it belongs to the training set the other k-1 times. So every data point is used for testing once and only once. This is what cross-validation looks like. Some of the features, it's a really good estimate of your out-of-sample error. The error that you literally cannot measure because it hasn't happened yet. It is a more efficient use of data than a single train test split to lose point. Just training and testing on one split can bias it. But if I do it 10 times on 10 random subsets, I get a much better overview of what's happening, and I average them out to a single number. It presents the trade-off between efficiency and computational expense. So in a tenfold, I'm actually doing 10 train test splits. I'm doing the model 10 times. And it can be used for parameter tuning as well. So if I'm not sure, is 7 neighbors better or 9 neighbors better? I'll do a k-fold for 7, a k-fold for 9, and see which one's better. So you can use cross-validation to compare my parameters. What does that look like? Let's see. Let's take another break. I'm sensing, is that, yeah, people are like, oh, thank God. Let's take another 10-minute break, and we're going to come back and go through the last coding sample of the day. 10 minutes.
Philosophical use case for variance and bias. So imagine you're a child.
Where?
And you're
I lost it a while ago.
yeah. But I mean, it like essentially like understanding how children can come to like kind of crazy conclusions or
They have a high bias. I'm talking about high variance and bias.
yeah. So like they could genuinely believe that there's like a monster in the closet because they don't have enough data to support it. It's not. Whereas older people who've gone through life and no monster has been in the closet have more, like their model gets kind of shrunk.
You're on the right track. The one
I don't know how to
issue I have with
explain
it is that the child has never accessed it.
What?
The child has never accessed it.
But it has less data to.
Fair enough. I see your point.
So like essentially the quantity of data like makes the child like more predisposed to believe that.
But the quantity of data is nothing with bias there. It's the number of predictors, or how complex your model is.
Yeah.
So I'm going to rephrase your example a little bit, okay? The child thinks there's a monster in the room because the mom forgot to put on the microphone.
And so
That's my like correlation. No nightlight, monster. And as the child grows up, it says, okay, well the nightlight's off and dad reads me a bedtime story, there's no monster. So it's just learning more about the environment. It's not just like taking in new data sets, but it is. But what it's doing is it's adding new features. And then after a while, it adds a lot of nitpicking. Okay, no nightlight, dad didn't read me a bedtime story, did not have a snack, and like I did brush my teeth. Just give me a monster. It's like learning, and that's getting weird now, but that's the point. Alright, a little bit.
Interesting.
It's not necessarily the data points, how many there are,
Yeah.
it's how many features he decides to look at.
Yeah. My other use case, and this will probably solidify it, is racism. So and
Also aware.
more so exposure to various ethnicities, like having a worldview, traveling gives you more kind of a larger feature set that people could kind of have.
Sure. If you say like this person is white, you're for bad.
Yeah.
But that's what you grew up learning, that one feature goes into the outcomes bad. And then later you learn, oh, when they're white and they're my teacher,
Yeah.
it's good.
Well,
Or something, you're
it's
adding
like-
more things. And
it's
then you
more like-
realize that
yeah.
race becomes irrelevant as you're adding more
Yeah.
features. But that's the idea. As you're adding more features, you're adding complexity.
Yeah.
And then you get to the optimal level of I understand what makes a good person.
Yeah.
And then you need to block race as part of that. But then as you start nitpicking, it's like, oh, someone, I guess, who's divorced. Someone whose parents are divorced, they're bad.
Yeah.
And you're like, that's really nitpick there. Maybe one person was the case, but
So it's like people who are like very like judgmental or like overfit or they overjet.
I would call this guy tend to underfit. because they're using less features to make adjustments.
Yeah.
Whereas, yeah, we'll get to that.
Got it.
Yeah, exactly.
Yeah.
So like the earlier you make a bias, the earlier like the child has experience, the way they have or they stay on here, but I have
Well, I guess machine learning and like bias.
Sure, I know what you mean. They are. They're related, but they're different definitions. Variance. It means literally when I talk about variance, it is the variance of the random variance. And that idea is still the same. But when I talk about variance, I mean variance of the distribution of how stable the model is. Specifically to a variable, or how much the variable is model changes. So it is a variance. I'm just using it in a very specific way. Kind of, yeah. I model my random variable. You get it all over the place in the distribution, and that's a high variance. You expect if the distribution is very spread out, you have very high variance. Like, if my model, like here's my expected model, like, here's what I expect the model to be.
Okay.
If it looks like this, it is a very low variance because it always does what I expect it to do, like the line. It's pretty much always where I expect it to be. And it's also, you can literally look at it like it's a small standard deviation, therefore a small variance. That's what I mean by variance. And then for bias, that's a little different definition, but bias you can think of like an error term. Almost like an error term. In fact, they even define it in the bias. They define it
as bias is like the ability of your model to represent the data that it's already seen. And variance is the ability of the model to represent new data, like how much it changes.
Yeah. Yeah, so here, bias is the expected of what I put into the model minus what it actually is.
Are there other
So
words?
bias is literally an error term, but specifically, it's an error term to your training set, not to anything else.
Interesting.
The reason I don't explain it that way usually is because both of them are compared to the training set. So it sounds like variance is not related to the training set, even though it is. I don't know. I hear a lot of different ways of explaining it.
It's
I
really
see.
tough concept.
Really?
That makes sense. Okay. Cool.
It's hard.
Yeah.
It's good stuff though.
No, yeah.
Yeah.
So, in determining the complexity of the model, let's say one variable would be high bias.
Sure.
Right? And it's pretty curve, but I want to know how do you assess the space? Just say they are you're testing their contribution, then assuming that a combination of parameters, is there a way to assess the complexity of some things that the parameters cover? Is there like this? Right now it's very subjective. Just say there's one variable bias.
Well, I would never say that one variable. I would say that the combination of these variables is the bias. You know, it's up to us to figure out which one's bad.
So when you train something, how do you know how big the training is?
You generally say like 70% make up that line.
No, in the wild. How do you know
Oh.
how much in the wild is it?
That's a different question. I want to answer this fast, but yeah.
I'll look it up.
tough.
That'll give me an idea of what's biased and what's not, I think.
All right, let's get back to it. I want to make sure I get through this before 9:30. All right, model evaluation. First, let's talk about why we're even talking about train, test, split, cross-validation. Why? Because of one neighbor. When we fit and predict on the same data, we get a score of 100%, always correct. And that is the perfect example of overfitting. Its bias is so low that it's never wrong. Why? It's because it keeps comparing each flower to itself and saying, oh yeah, we're pretty much the same flower. In fact, we're exactly the same flower because they are the same flower. That's overfitting. So I made it have a low bias at the expense of variance. This model will not generalize well because all it's done is, in essence, memorize the training set. And that's it. It doesn't understand the nuances in the data. It just nitpicked enough. In fact, it just compared it to itself just for the sake of getting that number of accuracy up to 100. Here's how the train test split helps. I'm going to import from Sci-kit learn, so from sklearn.cross-validation, import train test split, line 25 of 06 model evaluation procedures. I'm going to use NumPy to make a random set of features, where the first column is 0 through 9, the second column is 10 through 19. That's my data. My response is even, odd, even, odd, even, odd, even, odd, even, odd. Just even, odd times 5. When I do train test split, line 35, it will give me two things. The training features and the testing features. So if I look at features train, 1, 2, 3, 4, 5, 6, 7, 70%. It took 70% of my a random 70% of my training data and said, here, train on this. And in turn, it left the remaining 30% to test on. Note the random order at which it took. Bless you. Note the random order. So it didn't just choose the first 7, it chose a random 70% and then the remaining 30%. Line 40 is a long line, but I want to break it down. Features train, comma, features test, comma, response train, comma, response test. 4 things. And that's going to equal the train test split of features, comma, response, and then an optional parameter called random state so that we all get the same split for the purposes of this lecture. So here's what happens. I'll show you. I run that line, line 40, which is split up into 2 lines. I run this highlighted line, and I've created 4 new variables. Features train is 70% of the training data. Note the training data are these 2 columns. Features test is the remaining 30%. And you should all have the same numbers as me because we've all set the same random state of 1. Response train is 70% of the response. Response test is the remaining 30% of the response. So it split it up into a training and a test set. The training was split up into the predictors of the training set and the response of the training set. The test set was split up to the predictors of the test set and the response of the test set. So let's do it for Iris. We have our x and our y from up here. If you haven't run this line of code, line 11, please run line 11 first. And then come back down and run line 51 and 52. It's going to split up x and y. X dot shape, as we know, is 150 rows and 4 columns. X are the predictors of Iris. X train is 112 rows. So the training set of the predictors is 112 rows. 112 divided by 150 is about 75%. It actually changes how much of the data set to choose based on how large it is. You can set how much you want to take with an optional parameter, but generally you can just let it go. Now, if 112 rows made it to the training set, how many rows will be in the test set of X? Someone raise your hand and tell me. Says. What? Congratulations. Yes, you're correct. 38. But this is the point. Of the 150 rows, 112 went to the training, the remaining went to the test. Same with Y train, 112, and then 38 in the test. Now, I'm going to take my KNN of neighbors 1, that thing that got 100% last time. I'm going to note this, fit it to my training data. So a line 63, I fit it to my training, and then I score it on the test. And now look, I fit it to the training, I scored it on the test, and it no longer overfit itself. Now we're seeing a more accurate 94.7% accurate. So here's a kind of silly example, but I think it's pretty good. Suppose you watch a soccer game and memorize their patterns. You watch the game if you really like soccer. The Turkish soccer team. If you rewind the game and then you're asked to predict the outcome, you would know what's going to happen. Which is why we look at one game and figure out what they do, so that tomorrow, when I play them again, I can somewhat expect what they're going to do, but I can't know for sure. And this has happened to me before in a bar. I was watching a football game, which I was not aware had already happened, and I lost a lot of money. Well, that's what happens when you don't really know football that well and you're in college. So, moving on. Does that make sense? So we're no longer fitting and predicting the same. It's not allowed to memorize anymore. It's not allowed. So step 4, we're tuning our parameter. So step 1 was split the data up. Step 2 and 3 was to calculate the actual accuracy, your error. Step 4, tune it. Make it better. Instead of 1 neighbors, try 5. Step 70, line 74, instantiate a new Sci-kit learn model with 5 neighbors. Same thing. Fit it to the training, score it on the test, 97.3. So you would say 5 neighbors seems to be doing better than 1 neighbor. Because I'm using a train test split, it is more likely that 5 neighbors will generalize to the real world better. But how do I know which one to choose? What about 4 or 6 or 7 or 32? Which ones do I know how to choose? Step 5 and 6, once I choose 5, I then train it on the entire data set. Once I am convinced that 5 is the best number of k, I then fit it to everything. So that step 7 is when I have 2 new flowers come in. Imagine, if you will, you're a botanist and you have 150 irises. Pretend that these data points are your intern running in and saying, I found 2 new ones, I found 2 new ones. And they give you the measurements. And then you ask, what are they? Did you write it down? And the intern says, I don't remember. Let's compare it to the other 150 to figure that out. And you subsequently fire them because that was a very simple job, was to write down the species of flower. But I'm stuck with only the data. So my out of sample data are now these 2 flowers, which I've never seen before. And then I predict those 2 flowers I've never seen before. And I get 1, which is versicolor, and 0, which is setosa, in the same order. Am I right? Trick question. Am I right? This is correct. Is flower 1 a versicolor and the second one a setosa? Was I right? Why are you saying no? We don't know. Correct. How can we know? I guess. What? You said if? So we're saying we don't. Correct. We can never know if we're right or wrong. That's the point of out-of-sample data. We don't know if it's right or wrong until the event is over. It's like tonight. If I have my model that says Apple will go up in price, the stock. Apple the price will go up in price. Apple the stock will go up in price $1 tomorrow. That's my guess, and now I'm going to act on it by buying Apple. That's my guess. I won't know if I'm right or wrong until the day's over. That's out-of-sample data. Data that I haven't seen yet, I'm acting on, and won't know how I did until it's over. Which is terrifying. Correct, BlackRock? Correct. Terrifying. All right. Well, using just one training set and test set is not good enough. Let's use cross-validation. Sci-kit Learn has built-in cross-validation. Hooray. From Sci-kit Learn, .cross-validation, import cross-val score. Cross-val score will tell me the best scores of my k-fold cross-validation. I'm going to instantiate a model with one neighbor. Here it is, K and N. Remember, K and N is a blank slate. It's a completely blank slate. Line 113 is a new line of code for us. Scores equals cross-val score. So I'm initiating my cross-validation with parameters K and N, which is a blank slate. My predictors, my response, the number of times I would like to perform it, 5, so I'm going to split it up into 5 partitions, and how I want to score it. As of now, we only know accuracy. So I'm going to score it on accuracy. And I'm going to run this line of code. What just happened was, in that brief millisecond, it ran K and N 5 times on 5 random trained test splits of the data. So to go back to our slides, it did this randomly 5 times. It took this blue, trained it, tested on the screen. Took another green, tested it, or trained it and tested it. Took another green, trained it and tested it. Did it 5 times. And here are the scores. The first time I got 97%, then 97, then 93, then 93, and then I got 100%. So if I want a general answer, I'll just take the average and say, on average, one neighbor does 96% accuracy. Does what just happened make sense? I'm doing a trained test split 5 times in a row to average it out. It's like saying doing a cross-validation of the class I'll ask this quarter of the class, and then a random other quarter of the class, and then a random other quarter of the class, and then a random other quarter of the class, and then average my results. Yes?
If you were to do it another 50 times or 100 times, you should expect.
If I do another 50 times, let's try it. Let's change CV to 50. Run it. Still pretty fast. My scores is now a list of 50 things. Notice how much it overfits. In each individual case, you could still overfit. So adding complexity to my cross-validation also leads to overfitting. And if I do my mean score, isn't that funny? It's pretty much the same. Because notice I have a lot of ones, but look, I have a 0.3 repeating, 0.6, 0.6, 0.6, and 0.6. Is it a coincidence that it's the exact same number? Yes, that was a coincidence. Let's try 100. Whew, I can't do that. 80. You're being mean. What? That was strange. I guess I've never tried to do it that high before. Alright, I'll try another number though. Here's 20 with a different number. Here's 20 times and actually get a better score. So you can tune your cross-validation, but do not do that. Cross-validation is not a model. Cross-validation is a means to evaluate your model. I guess maybe there's a restriction that it can't do more than a third of the data set, because the data set is only 150. I have to look into that, because I actually don't know. But it's a good catch. Now, but this still doesn't answer my question, which K? Still doesn't answer that question. To do that, I'm going to try several Ks and see what's best. I'm going to try all odd numbers between 1 and 29. If I do that, so to read this code, I'm making a list from 1 to 30, step 2. So the list is 1, 3, 5, 7, 9, 11, 13, etc. I'm initializing an empty list of scores. For each K, I'm going to make a new K-neighbors classifier of n neighbors K, and then do a cross-validation 5 times. And then add the score to scores. Pop quiz. How many times total will K-neighbors classifier run? Ozzy? Say it again? 15? Who agrees? Who disagrees? This is me raising my hand because I disagree. Why do you say 15? I mean K-neighbors classifiers. How many times does the actual single model K-neighbors classifier run? You said 15, Ozzy, because, you might correct me if I'm wrong, there are 15 values that I'm looking at. 1, 3, 5, 7, 9, 11, right? Correct? For each of those K, however, how many times do I run K-neighbors classifier? 5.
You're not talking about line 130 K-neighbors classifier. You're talking about actually bidding the model.
If I wanted this, I would have asked, how many times do I instantiate a model? And the answer would have been 15. But how many times does it actually run, like predict stuff? And that is 65. 15 total Ks, 5 each. So it runs a lot. That was incorrect. 75. Just, math is hard. Even if you have a master's in it. Math is difficult when you're tired. 75 times K-neighbors will run, fit, and predict. So let's take a second, and I'm going to count it down, and we're going to see how fast it can do it. So I'm going to 3, 2, 1, run. 3, 2, 1, go. Okay, pretty fast, but note there was a lag time. Later on in the class, when our models get much more complex, this time will take anywhere from 1 to 5 minutes. There are people whose projects are like, yes, after cross-validating it 10 times and waiting 3 hours for it to work, here's my model. Yeah.
So when you're actually using that, run it 3 times.
Yes. And I will do that in the class. And I will time it, which will do it in times 3. A lot. So what I'm looking at are the scores for each value of k. Here's the cross-validation for 1 neighbor, 3 neighbors, 5 neighbors, 7 neighbors, 9, 11, 13, 15, so on and so forth. But I don't like looking at it. I'm going to plot it. Look at that. Now I'm going to spend some time here. By some time I mean a couple minutes. What we're looking at is the x-axis is the number of neighbors. The y-axis is accuracy. What can you tell me about the accuracy as I add a number of neighbors? What's happening to accuracy? Before it goes down, what does it do? It goes up. It starts here, and it goes up for a little bit, and then it goes down. What is the x-axis again? What is it? It's k. What else could I call it? N underscore neighbors. What else could I call it? Model complexity. As I add to n neighbors, I'm adding to the complexity of the model. As I add complexity, what happens to error? It goes down until the optimum, and then it goes back up. It gets better as I add complexity, and at a certain point, I'm nitpicking, and it goes back up. Yep. Why?
Low K is high variance.
Thank you for bringing this up. Do you agree with this graph?
Call in reverse.
Well, do you agree with this graph? Forget the K. Linear neighbors per second. As I increase complexity, my error will go down until I'm overfitting, and then the error goes back up. Do you agree with that? Well, you have to. I'm the teacher. You know. But this is true in general. As I add complexity, the error goes down and then back up. So you're saying that's the opposite of this? Is the y-axis error? What is it? It's accuracy. It's accuracy. Actually, different things entirely. Bias is not the same thing as accuracy. They're related. It is a type of error, but accuracy is specifically how often it's right. I'll argue, as error goes down, what will happen to accuracy? Goes up. So what you're looking at is the inverse of this graph. In this graph, as I add to complexity, the error goes down and then it comes back up. This is the same graph, but instead of looking at error, I'm looking at accuracy, which are related. As error goes down, accuracy goes up. So as I add complexity, the error of my model, the error is going down. Therefore, the accuracy is going up until a certain optimal point. At a certain optimal point, the error starts to increase, thereby decreasing the accuracy of the model. Does that make sense? Yeah? What's your question?
Yeah, so this is the mean of those 5.
This is the what?
This is the mean of.
Yeah, so each data point is a mean of 5 k-nearest classifiers.
In my head, I guess, at least, I'm thinking that of that more as bias, and the standard deviation of those 5, I would think is more as variance.
Well, you'd be correct because variance is standard deviation squared.
Yeah. So I guess I just correlate that more to bias than total error. But
Well, bias and error are related. And I don't want to, they're not the same thing, but they are related. Bias is a type of error. Error is a very general term. Yeah, error, that's one definition. What you were about to say is only one definition of error. Error is just incorrectness of model. You can define incorrectness several different ways. You could say I'm incorrect if I classify the flower wrong. You could say I'm incorrect if I'm more than $5 off the price. You could say I'm incorrect if I'm only $10 off the price. You can define error however you want. I'm defining error to be 1 minus the accuracy. Does that make more sense now? Does it make sense in general how this graph right here, how the accuracy goes up and down, is related to the graph where the error goes down and up? Cool, right? Yes, it is. But that was really involved. And so we haven't picked one yet. Which is the best? We still haven't even picked the best one. You can make an argument where it seems to be between 11 and 7. 7, 11, the best numbers in the world. 7, 11 seem to be the best parameters. Which one should you choose? In general, if you have a tie, it generally goes to the less complex model. We like less complexity, contrary to popular belief. We actually like it when things are not complex. Sometimes we have to make it complex. We don't like that. So I would pick 7. There's a way to automate this, and this is the last thing I'm going to show you today. It's called grid search, and it's awesome. What grid search does is that you tell it a range of parameters that you want to try. It tries all of them, and then it gives you the best answer. In this case, I'm going to ask grid search to try between 1 and 29, just like before. The way it works is, I import, from sklearn.gridsearch, import gridsearch-cv. Grid search is the thing that it tries all possible combinations of parameters. What do you think CV stands for? What do you think? Cross-validation. Stands for cross-validation. So it's going to try every single parameter combination, and it's going to assess how good it is using a cross-validation. It's pretty much the creme de la creme of model tuning in Sci-kit Learn. Not only does it try every combination, it tries every combination the best way possible using cross-validation. So this is a preferred way of model tuning. Would you guys agree? TAs? Is that what you guys generally use? But in general? In general, yeah, I'm getting thumbs up. So, but you're right. Say it again?
It's better than finding it yourself.
Better than finding it ourselves. Totally agree. Especially when there's more than one model or more than one parameter. So I'm going to make a k-neighbors classifier. Notice I'm doing even less here. I'm instantiating a k-nearest neighbors without telling it n-neighbors. I don't even tell it n-neighbors this time. I make a k-range, which is just a list from 1 to 29. I make a parameter grid. A parameter grid is just a dictionary. It's a fancy term for a dictionary. Where the keys are the names of the parameters I want to tune. In this case, n_neighbors. And the value is a list of the options I want to try. So in this case, I'm only going to tune one parameter, n-neighbors. I create a grid search object by doing grid equals grid search CV, and the parameters are my k and n, my parameter grid, the number of times I want to do cross-validation, and the scoring. It's a very similar to cross-validation parameters, except the big difference here is instead of telling it, instead of doing one k, I'm telling it to choose between all of these parameters. And this will become very handy when we have 5 parameters to tune. And it's going to try all possible combinations of all 5 parameters. And then I will fit. Again, what this just did was 75 k nearest neighbors. It just fit and predict 75 models in a row. 15 Ks, and for each K, 5 times. If I had chosen to do for all, 1 through 30 without going by 2, it would do 150. This doesn't math. All right. So, grid now can show me the grid scores. For each K, it'll show me the mean, also the standard deviation, and the parameters. So when n neighbors was 1, it got a mean accuracy of 96 with standard deviation 0.02. And then so on and so forth. I'll take the mean scores, plot them, and get the same graph as we got on our own. This is the same graph that we just got doing it by hand. Grid search got the same thing, which is good. We wanted it to get the same thing. It can also show us the best score, which was 98%. The best parameters, which was n neighbors equals 7. So of the 711, it chose 7, which was the lowest complexity. And it even has a way to actually output the model that was the best. And grid search will be our preferred way of model tuning. In an instant, we'll try every single possible variation of the parameters you tell it to, and for each possible combination, run a k-fold cross-validation. It's the creme de la creme of model tuning, yes.
It outputted a number of parameters, but it only tested the in underscore neighbors.
Because I only told it to.
Right, but you can
So,
tell them to do it.
I will finish on one more sentence to answer your question. Look at this, k-nearest classifiers. Look at all the stuff inside that I haven't even mentioned. Those are other parameters that I chose not to tune. Algorithm equals auto is a parameter that essentially dictates how it chooses the neighbors. Leaf size equals 30. What is leaf size? I don't know. Hold on, I'll get to that though. Metric equals Minkowski. What in the hell is Minkowski? I thought it was Euclidean distance. Does anyone know what Minkowski is? Be very surprised.
It's like a combination of Euclidean and actual distance, so I think it's all.
Kind of. Minkowski is the generalized Euclidean distance. So you know how the distance formula is x1 minus x2 squared, this thing? Right? Distance formula, including distance. Well, if I replace this stuff with a variable, the pth root of x1 minus x2 to the p plus y1 minus y2 to the p. This is Minkowski of order p. It's a generalized Euclidean distance. When p is 2, it becomes the metric that we know as Euclidean. In fact, you'll even notice as our metric down here, p equals 2. So by default, Minkowski of p2 is the Euclidean distance that we know. Whoa. As an example, if p were 1, it would look like this. You would just have x1 minus x2 to the 1 plus y1 minus y2, and then the 1th root, which is just nothing. So this is Minkowski of p1. You just add it, you're subtracting the variables and adding them up. And all that does is tell you the literal difference between each point. As I add to p, I'm just punishing bigger weights by putting it in a bigger scale. The point is, you could have changed Minkowski. You could have tried p from 1 to 100. You can tune all of these parameters, but it'll only tune the ones that I tell it to. That's enough for today. My head even hurts. So have a great. You ever want to?
I just want to
In general, metrics are very dangerous because of scale of data, and we'll be aware of that as we move forward.
One thing I just want to make on that one metric that is public practice is cosine distance. That's actually I found that more popular.
Sure, and we'll talk about several types of distances in the class. Euclidean will just be like our baseline, but there are different types of distances. Have a great night. I'll see you on Monday. The homework, which I believe I did, essentially work on your project. You're going to be getting feedback from us on your one-pager / your Python file by next week, but start working on whatever it is you wanted to do. You should start working on it as early as possible. There is some other work and some resources to understand train test split and overfitting, underfitting. Otherwise, I'll see you on Monday. Bye.